Okay, so for my video, I'm going to solve problem 1. And the first thing it asks you to do is draw the free body diagram. I decided to draw it to the side instead of already drawing it on here. That way I would have my X and Y plane already labeled out instead of having the weird sideways going on. So the first force is the applied force, and we don't know what that is yet. And then you have the force of gravity, which is going 25 degrees this way. Because if you were to redraw this, this is 25 degrees, and then this angle would therefore be that. So we have the force of gravity going this way. I could rewrite this as two separate forces, with the one being the cosine going down and then the sine going that way for that angle, but I'm just going to leave it like this. And then if we were to add the cosine of this force plus this force, we would get the normal force going upwards. So that's our second to last force. Then we have the force of static friction, which is going this way, which is just the the coefficient of static friction times the normal force. So that's my free body diagram. Then the second question asks you to write down the Newton's second law equations for each relevant axis. And so going back to this diagram, I started with the y-axis, and I already kind of explained that. So to find the total force, you would just add up the cosine of this angle times the force of gravity, which I have here, and the force of gravity is mass times gravity, of course. Plus the applied force, which we don't know what that is yet, which is this, and then you would subtract the normal force, and that would give you the total force for the y-axis. I could say this equals 0 since the object is stationary. I didn't write that yet. I don't know if I'm supposed to write that or not. And then for the x-axis, we would have the force of gravity times the cosine of 25 to get the part of it that goes this way. Force of gravity, mass times gravity, so times the sine. Did I say cosine? I don't know if I did, but I meant sine. Minus the force of static friction. And that should also be equal to 0 since it's not moving. And I put little notes on here about what equals what. Like the normal force is equal to the applied force plus mass times gravity times cosine of the angle. And then if you do the normal force times the coefficient of static friction, you get the force of static friction. Then for the third question, it's asking for the value of the applied force so that the block will remain still. And to solve that is kind of a nice little problem here, because you'll do the applied force plus the force of gravity times the cosine of the angle. That way you have the y part of that. And you'll add those together to figure out what the normal force is equal to. So you have to do that first. So we know the normal force equals gravity times cosine of the angle times mass plus the applied force. And we don't know what the applied force is yet. So we'll have 9.81 meters per second times cosine of 25 times 2 kilograms plus F, and that comes out to this. And we'll leave that alone for now. And then we also know that for the object to remain still, we need the mass times gravity again times sine of the angle for the x part of gravity's force. And we need that equal to the coefficient of static friction times the normal force. And once those are equal, we know that the object is stationary. So I just rewrite that here. And then if you write that out, you get 2 kilograms times 9.81 meters per second squared times the sine of 25 equals, there's our coefficient of static friction, 0.22. And then I rewrote the normal force from a minute ago. So I rewrite that there. That comes out to this. Then divide it on both sides, got that. Subtract that from that. And now you solved for the applied force, so the minimum value needed for F so that the object remains stationary is 19.9 newtons. And then for the last question, it's asking if the applied force is removed, how fast will the block slide? And so I redrew my free body diagram to where I got rid of the applied force that goes down. And since that goes away, your normal force is going to change now because you don't have the force of gravity times cosine of theta plus that applied force. So now you'll do, how do I write this out? First I solved for the force of the kinetic friction. So to get that, you would have to do the normal force times the coefficient of, that should be a K, times the coefficient of kinetic friction, which is, the normal force is just equal to the force of gravity times the cosine of the angle. So you do mass times gravity times cosine of this angle, which is equal to the normal force, and do that times the coefficient of kinetic friction. Again, I messed up there. And then you'll do, so that'll be 2 kilograms times 9.81 meters per second squared times the cosine of 25 times, there's our coefficient, 0.18, and that comes out to 3.2 newtons. So that's how much the force of kinetic friction is, and it's going in that direction since the motion's going this way. Oh, and then we need to figure out how much gravity affects the force going this way. So we have the mass times gravity times the sine of the angle. So you have 2 kilograms times 9.81 meters per second squared times the sine of 25. That's 8.29 newtons going this way, while you have that 3.2 newtons still going that way. So you would just subtract the two, and I wrote that out right here. So 8.29 newtons minus 3.2 newtons is 5.091 newtons, and that is equal to the mass times the acceleration of the block when it's sliding down the ramp. So you would just simply divide by the mass of the block, which is 2 kilograms, and that gives you your final acceleration of 2.54 meters per second squared.